Hello everyone, welcome to my Programming Club. Today we will be solving another daily LeetCode problem, and the problem's name is step by step directions from a binary tree to binary tree node to another. Okay, so you will be given the root of a binary tree. Okay, and there will be n nodes in this binary tree. Each node will be uniquely numbered from 1 to n. Okay, uh, they will be assigned a value, and then you are also given an integer start value representing the value of the starting node from where you will begin your search for the destination node. Okay, and a different integer will be given which will be the value of the destination node. Okay, and so you have to find the shortest path starting from the starting node's value, node with value equal to start value, and then you have to end your path to the destination node which is having value equal to destination value, and you have to find the shortest path. Okay, and while you will be traveling the nodes or traversing this path, you have to write the directions. So for example, if you from the current node, if you went to the left child of the current node, then you will write L, or if you went for the right child, then you will write R, and if you went for the parent of the current node, then you will write U. Okay, and each letter specifies a direction. As I have already told you, L specifies that you are visiting the left child of the current node. R specifies that R means that this right child is visited for the current node, and U means that parent of the current node is visited. Okay, so you have to return this step by step directions. Okay, so this is the this is one example. Okay, so let's have a quick look at the constraints also before thinking of an approach. So the number of nodes in this tree, which is equal to n, will be of order 10 raised to power 5, and nodes value will be ranging from 1 to n. Okay, and all the values are specified to be unique in this particular binary tree, and start and destination values also will lie in the range of 1 to n, both inclusive. So, and it is mentioned that the start value will never be equal to the destination value. So start and destination node will never be the same. So these are the constraints. So let's think of an approach. So let's take this one example to see how we can approach this problem. Let's zoom in a little bit. So what we will be doing here is, as you can see, if there is a path between two nodes, it will indeed be the shortest path. I mean, there cannot be multiple paths, because if you start from, in every node you will be having three choices. Okay, three directions to go. So let's say 3 was having something. Okay, so left and right child were not present for 3, but its parent was present. Okay, so either you can go to the parent, or you can go to the left child, or you can go to the right child. Okay, so this is what you have to do for every you can do for every node, the choices you will be having. So as you can see that if you are to reach 6, then there is no another way that you can 6 from, because since it is a tree, so there will be the only way will be the shortest way possible. Okay, so we need not to worry about being of finding the shortest path. Okay, if we are only traveling in these directions, I mean, if we are not forming a loop kind of thing. For example, let's say you went in this direction, and then again you visited 3. Okay, and then you keep looping around this edge. So if you are not looping around, then you will for sure find the shortest path. Okay, and the only path that you will find will be the shortest path. So you should not run in loops, should avoid loops basically. Okay, so if you have already visited your nodes while traversing some paths, then is it it's you know mandatory to avoid that visiting that node again, because you have already visited all the possible paths for that node, and it will only result into loops. So we should be avoiding loops, or you can say path loops. Okay, so this is one observation that we have to make, that we are having three choices and we should be avoiding loops, and if we do that, then we will for sure reach the destination node and we will get the shortest path. Okay, so but now the problem arises that we were given only source and destination, start and destination values, not actual nodes or addresses or the references. Okay, so start value was given to us and destination value was also given to us, but we were not given the actual references or the addresses of these nodes. So for that we have to, you know, find the actual references or the addresses of these nodes in the tree. So you would also like to make some links, because you know by default only these kind of links are present. So let's take the bigger eraser. So only this direction is available to you by default in the tree. Okay, downward direction, you cannot go up. Okay, in downward you are definitely having two choices, either you can go to the left child or the right child of the current node, but you are not having link to the parent. Okay, so for that you have to build those links. So another thing that you have to do is, let's break it down into step by step manner. First of all, you have to form parent links. Okay, in order to facilitate yourself to go in up direction from the current node. Okay, so this is one thing. Then you have to just start from the start node. Okay, so while forming the parent links, you will be also finding the values of start node and the destination node. Whenever you are visiting a node whose value is coinciding with or equals to either of these start node or destination value, then you will update your start node and the destination node, uh, whatever the situation is. If the value is of the current node is equal to the start value, then it's the start node, and if it is equal to the destination node, then it's the destination node. So this part is already taken care of. For this part you can use a DFS. Those of you who are hearing the word DFS for the very first time, it is nothing but that we start from a point and go in the depths of the current path till we encounter a situation where we cannot proceed further. Okay, then we traverse back one step each time and try to see if there are any other paths possible. Okay, so this is what happens in a DFS, although I will also provide some articles link on DFS, so you can definitely check it out. So now moving forward, we will be starting from the start node, then we will be visiting and ending on the end node. Okay, or the destination node you can say. Okay, so by discovering all these possible three directions, either you can go to the parent, current left child or current right child. Okay, so these three options will be always available for you, and other than that, this thing will also be done with the help of our DFS. Okay, so now you may ask, like, how we will be keeping track of in which direction we are going, and so for that what we can do here is, For that, let's say these are some details of the implementation part. For that, I think it will be better for us to bring the code also on the slide so that we can have a look, and it will save us some time. Rather than explaining the code separately, let's discuss from this point forward, and it will be a little bit easier for me to make you understand the approach. So let's take a fresh slide and bring the code here. Okay, I think the code is a little bit long. Implementation wise, it's somewhat long, but logically it's very easy. So I think if the code is that much long, so we should be uh, what should I think let's start from here. So what we will be doing here is, let's clear the board a little bit. Let's see how we can keep track of the directions we are going. Okay, so now supposing that we have formed the parent links already, and we can go in all three directions, and we are also having addresses of these two nodes. Okay, these two. So we are starting from our start point. So this is our start node. Okay, and starting from our start node, we will be traversing all three, checking all three directions. So this is the parent direction, and it's the left child direction. Okay, and this one will be the right child direction. Now you will ask that how we will be keeping track of the directions that we went. So for that we will be using a stack. Okay, so first of all, you can pick any of the directions. Let's say I picked the left child first. So we decided to explore the left child. Okay, so we ran a DFS call on the left child, and at a certain point, if we are not able to find our node, the destination node, let's say our left child call returned and we didn't reach the destination. Okay, so in that case our stack will be having some values that we have, some direction values that we have taken. Let's say we have taken left, then right, then left, then right. Okay, somewhat like this. So each time you are taking one step back, or in that recursive call that you made, let's say this was the kind of the recursive call that you went through. Okay, so each time you are taking one step back, you should be popping this value out of the stack, because it is of no use to yourself. You have already checked that this path is not leading you to any answer, so why keeps directions in the stack? So this stack is nothing but, if you go in this manner from bottom up, then it will be your the directions that you have to take to reach the whatever the node you are currently at. Okay, so since you are backtracking or going back each step, so you will no longer lead these directions. Okay, so you can pop these out. So this is how you can keep track of the directions that you went through. And if let's say at a certain point you reach the destination, and your obviously if you reach the destination, your stack will not be empty. You must have taken some uh, directions, like either you have went to the left child, right child, or the parent. Okay, something will be there in your stack. So if let's say the stack is having something, let's say it was like up, then right, then left. Okay, something like this. Then your answer will be, the shortest path will be, directions for the shortest path will be this way up. Okay, because stack stores in last in first out order. Okay, so LRU URL will be your directions. Okay, so as when you reach the destination node. So this is the whole logic. I repeat, the first step was to form the links for the parent, and also to find the addresses of these two nodes, the start node and the destination node. Okay, these two nodes addresses are have been found, and these links have been made. Okay, these kind of links. So after doing so, we started our journey from the start node, and we checked all three possible directions and used the stack to keep track of the directions we went through. Okay, and once we reach our destination, then we empty our stack uh, and treat is like a queue, okay, and store our result in the bottom up way, okay, because the stack is storing this way only. So once you do that, you will be having the directions for the shortest path possible from the start node to the end node. So let's have a quick look at this implementation also. So first of all, as I discussed, you should be, first of all, you will be making a map to make those links with the parent. So it will help us to make parent links. Parent links. Okay. So once we make those parent links, what we will be doing is, first of all, you might be wanting to see how we are making those parents link. So this is the graph which will be the method basically which will be helping us to make those parent links. So let's see what's happening inside it. So this is the method that was helping us. First of all, you will begin from the root, and then you will traverse the whole tree. So once you are traversing the whole tree, then you will be storing your start value and the destination value in some global variables like these. Okay. Or you can pass these down also. Here I have passed them down, and the start node and the destination node are declared in global scope. So here you can see. Okay. So these will be updated once we find the nodes equal to the value of start value or the destination value. We will update these nodes accordingly. And for the making the links between the current node and its parent, we are using this graph. Okay. So if the left child exists for the current node, if there is a left child for current node, then you will make the link between the left child to the current node. So the current node will be its parent. So you are doing so. Then you are recursing for the left subtree. Okay. And similar thing you will do for the right child also if you are having a right child. Okay. So once you are done with making the links and finding the references or the addresses of these start nodes and the destination node, then you will proceed further for the next step, which is to start our journey from the start node and end it on the destination node, okay, which will also be a DFS call. So this function was nothing but a DFS, depth first search, and this next function is again a DFS. Okay. And in order to avoid loops, we will be using a set to keep track of the nodes we have already visited, in order so that we can be sure that we are not running into a loop kind of situation. Okay. So then find path will help us to make find the path that will be leading us from the start node to the destination node, and it will be taking couple of parameters. The first parameter is the current node that is being visited. Initially the current node will be starting from the start node. Okay. So we will be starting from the start node, and you already know what is the destination node. Okay. And then you are also having the links between the nodes and their parents. Okay. So so that you can visit all three directions. So once you have reached your destination, if there is a case that your current node is equal to your destination node, then you will simply form the path then and there, and you will return, and knowing that you have found the shortest path possible. Okay. So as I talked already told you also, if the stack is something like this, then our answer will be ULR. Okay. Because it will be stored in bottom way up. okay, bottom up manner. Okay, so you will make your shortest path. This shortest path is declared here. Okay, and if it is not the case that you have not reached your destination node right now, then you will explore all three options possible. So either you can go to the left child, or you can go to the right child. Okay, or you can also go to the parent also. Okay, so these three options will be there for you. And once you are done with the recursive calls of the all this, you will pop the elements out of the stack, because they are no use to ourselves after we have you know, traversed back from the current step in the DFS call. So you will pop the elements out. Okay, that's why we are popping elements or the directions out from the stack. So once you have, you know, completely run this particular method, then you will be having your shortest path, and you will be simply returning that shortest path. Okay, so it was a three-step process. The first step was forming parents link. Okay, let's change color here. So first you found the parents link, and along with that you also found the values of the start node, and or addresses of the start node and the destination node. Okay, or references here, references of start node and destination node. Then the third thing was to just start your journey and explore all three possible options starting from the start node. Okay, start your journey from start node. And along the journey from each node, you were able to go to three directions. One was up direction for the parent, and then left direction for the left child, and right direction for the right child. So this is what you have done. And if we talk about the complexities, so let's take a fresh slide for that discussion. Time complexity wise, it will be order of n. Okay, where n is the number of nodes, because we are visiting each node for a constant number of time in both of these DFS calls to these separate functions. One was for making the links and finding the references to the start and the destination node. Another DFS call was to find the shortest path. So in both of these we were traversing each node constant number of times. So time complexity wise, it's linear, or you can say order of n. And space complexity wise also, it's order of n. Okay, because uh, whatever you consider, either the recursion stack or this stack that we are using to find our path, or this even this string builder also, which is being used for storing our shortest path, our result is still using linear space. So these are the complexities. If you are still having any kind of doubts or any queries in general in the approach or the intuition or anything you may like, so you can ask them in the comment section. I really hope this solution walkthrough added some value to your journey of honing your DSA skills, and keep solving more and more problems. I will see you in the next video. Thank you for watching.